My name is Bianca Peters, and I am the president of the Squamish Historical Society. The reason you are all here tonight is because we are now in the October section of the Squamish Historical Society Speakers Series for the fall. So we're going to be having Dr. Steve Quane from Quest University, Canada, speaking, reprising his role, speaking about the history of geological history of Squamish. He was the plenary speaker in 2012. And actually, I'll read you a bit of his bio. We cover that in that. Let me see. So, the Geological History of Squamish with Steve Quane. Steve teaches at Quest University, Canada, and holds a PhD from UBC in experimental volcanology. After completing his studies, he was selected as the American Geological Institute's Congressional Science Fellow and served as a science advisor for then Congressman, now U.S. Senator, Tom Udall. He taught for 3 years as a visiting assistant professor in the geology department at Colorado College and taught field courses in Hawaii, Mexico, British Columbia, and throughout the U.S. Southwest and Yellowstone National Park. His presentation will focus on the geological foundation of the sea-to-sky corridor and will offer singular insights into the ever-changing physical environment we call home. Ladies and gentlemen, I now present to you Dr. Steve Quane.
Well, thanks everyone for showing up. Can you hear me back there?
Yeah.
Great. Okay. Oh, sorry. For the students in the audience in my class, normally try to spell things correctly on your opening slide. We do things a little bit differently at Quest, but not that different. So I just wanted to thank everyone for coming tonight. I really appreciate the turnout. It's really fun for me to do things like this. Living in this area as a geologist, someone who studies volcanoes, is absolutely precious, and I appreciate other people in the community wanting to know about where they live, and I also appreciate the Squamish Historical Society having events like this to help connect the people of the area with their community in many ways, including the natural world that we live in. I've had a great day. In class today, I have students working on research proposals, and they're doing all sorts of crazy, great things. They come up with their own ideas, and a couple of them are going to save Brackendale from the next flood. One of them is going to make sure the dikes are high enough, and the other is going to help with the resistance or the resilience of the community for when the flood, if it does happen. One of the more wayward ones is we have all in geology. We love these big landscapes. We love to go on field trips and walk around and drive around the big open spaces, but he just decided to look at geological history through gene mutation in microscopic bacteria or something like that. So that's a little strange for me, but fun to be involved with. We have others, wanting to save the world in a lake in Peru. One's going to go to the South Pacific on a cruise to look at the subduction zone there. We have another taking a good hard look at the wood fiber site, and then one sort of novelty is trying to solve our energy problems with logic and reason, which I have yet to see in my political days. I certainly didn't see much of that. There must be others. Oh, we have one who's so obsessed with soil mechanics that she doesn't really know what to do with herself right now, which is certainly fun to be involved with. And then, if I missed anybody, we have another one trying to find more diamonds so we can build another building at Quest. We have a rich history of using diamond money for great things, or we think they're great. I don't want to leave any of the students out here. Climatology, right? It's something about saving the world from climate change with a mathematical model. Minor project. And I think then there's one who wants to use some sort of newfangled laser flame device to blow up boulders and help miners who leave big boulders in the way after blasting. So that's something I certainly wouldn't have assigned as a project. So it's really fun, and then I enjoyed the day, got to go out to have a trail run on one of my favorite trails and sort of think about the geology, and then it's Thursday, so there was a faculty meeting. And I don't know, maybe if you've ever been to a faculty meeting, I was thinking today how to express it, and it's sort of like you have a family reunion for Thanksgiving, which is coming up, and so you have about 35 of your family members. And imagine a faculty meeting is the time when you have to take that picture of the whole family, but everybody in the family is qualified to take the picture, and you have to discuss where you're going to take the picture. That's sort of like a faculty meeting. So all of this great stuff has really gotten me through that part of the day. And again, I just wanted to thank everybody for coming tonight. And if you'll indulge me, I'd like to talk about a few things and then nerd out on some pictures of rocks and tell you how we think we know what's going on in the surrounding area. And so this is Garibaldi Lake. How many of you have been up to Garibaldi Lake? That's pretty good. If you haven't been there, head up there tomorrow. It's a wonderful place. We really have a good partnership going with BC Parks. Katie Chambers and Vicki Haverhill have been instrumental in starting some research projects with Quest, including at Garibaldi Lake. And it's a huge lake that really shouldn't be there. There's a conspiracy of geologic events that happened that I'll talk a little bit about later that allow this lake to sit up at about 1,470 meters of elevation. I think right here we're at about 25 meters of elevation, something like that. So 1.2 trillion liters of water perched up there 1,400 meters above us. And so that you might consider that a geologic hazard. I had to I was trying to figure out how much water 1.2 trillion liters was, and I thought, okay, an Algene bottle is about a liter. Then I realized that it's like 3 million beers. So that really allowed me to put it in context that I understand. And so I did a sort of a back of the envelope calculation of if the barrier, which we'll talk about in a minute, it's a lava flow that holds up this lake, if it instantaneously collapsed, which geologically is going to happen, we probably don't need to worry about it, but in our lifetimes. But if that collapsed, I made some calculations. I did some assuming of things and simplification. But what I realized that here at the Brackendale Art Gallery, if it collapsed, we'd have about a 250 meter tall wall of water that rushed past us faster than Usain Bolt can run. So, and it would last between a minute and a half as it rushed through. Of course, as my students were arguing with me the other day, that's an oversimplification of the model, but I think the point is that's a lot of water, and most people who live in places don't need to worry about things like that. Perhaps you were one of them living here before I just said that, thinking as you go to sleep tonight, well, at least it's going to be quick. So I wanted to talk a little bit about sort of how these things happen and how we know they happen. So what do we do as geologists in the field? What do we look at, and what does that allow us to say about these natural features? And think about, as a geologist, as a scientist, you're putting together the best idea, and you're hoping someone comes along and improves it, or even discredits your idea so science can advance forward. So these aren't sort of the answers. I'm not giving you the answers. I'm giving you what we think happens and a little bit about why we think it happens. And so if you don't agree with what has been said, these are the people who came up with a lot of the ideas. So I put this early in the talk, so if you don't agree with it, you can remember. I also put it on the talk. If you like the talk, then you'll have forgotten all these people and probably figure I did all the work. But Pierre, I never know how to pronounce his name, Freely. He's a local guy. He's got a great geology beard if you ever get a chance to meet him. And then John Clegg from SFU has done an amazing amount of work in this area. They've produced, and him and Bob Turner have produced some of these excellent approachable books about the area. And then some mapping was done by Andre with a French last name. And then there's many people who contributed to this area. This is not an exhaustive list. This is just sort of some of the references that I was using. But Bill Matthews was a real inspiration. He must have been in canoes and on horseback back in the 50s up here, mapping Garibaldi volcanic complex and Garibaldi Lake, which is something that I plan to embark on for the next 5 or so years of my research, assuming BC Parks gives me the permit. I did mention our nice collaboration earlier, didn't I? Okay, so here's sort of how I frame what's going on in this area, and I look at it in sort of the first 4.4 billion years of life, or Earth, very little life actually. We don't need to worry about that. That's the old stuff. We'll just disregard all that Earth history, and we'll start at about 100 million years to the present, and look a little bit into the future. And so I see it as sort of mountains were built, ice filled in those valleys, and then fire and ice or volcanic eruptions interacting with those glaciers, and then that creates a whole unstable system of things perched high up in elevations where they shouldn't be, and they start falling down into the valley where we all live. And so I started to think about this. Is sort of geologic time is one of those things that you can never really understand. It's a crazy concept, this deep time. And so I sort of stole something from someone else and did a few quick calculations to put what we're looking at into perspective. So can I have an average sized person come up here? Not everybody at once now. An average size, like a 5'8" female is who I measured at work. There we go. Woo! There's some stairs over here too. All right, if you want to stand right up here and just put your arms out to the side, like fully out. Okay. So and then yep. There we go. Okay. So if this is geologic time, this is the beginning of the Earth. This is 4.5 billion years ago, and this is today. And so if we think about, I just want to put a few major Earth events in context. Uh-oh, I'm showing you the good stuff. Right, so your right elbow would be about the oldest known rocks. So about 3.8 billion years old. Bacteria have been found in rocks, and then the oldest known rocks are a little bit older than that. But so essentially, from the formation of the Earth, these are the oldest rocks that we've found on the Earth. If we think about when the atmosphere was oxygenated, that's about at your right ear along the time scale. Your left wrist, all the way down here at your watch. So all this time, 542 million years ago, was the Cambrian explosion. So really when life as we sort of know it started to happen in the oceans. Dinosaurs, everybody's got to know about the dinosaurs. So at your wedding band, right here, was when dinosaurs were first known to be on Earth. And then the last knuckle on your left middle finger, right there, was, well, of course, when the Chief was formed, 100 million years ago. So everything I'm going to talk about tonight is essentially in geologic time from this last little knuckle to the end of her finger, right? All of this stuff somebody else can worry about. We don't have much of that in Squamish. I'll keep it, we're almost there. 2 more. There's a manicure at the end. So it's worth it. So the cuticle on your left middle finger, if I'm right, that's where your nail starts, right? Cuticle. Is the mass extinction, essentially at the end of the Jurassic, where all the dinosaurs died. People think it was a meteorite impact. And the distal edge of the nail plate on your left middle finger, the distal edge, so like the end of your nail, was when sort of humans, as what we see as modern humans, you've given up on that part of time too. Okay. And then if I took a nail file and gave her a pedicure, pedicure, I didn't take your shoes off. That's good. If I just took one swipe with a nail file, that's the last 10,000 years. And that's most of what we're going to talk about in the presentation tonight. Thank you very much. I would like to say that you're average, but only in your size. Everything else, well above. Okay, so we're going to sort of talk about these processes in that order, and I'll keep coming back to that time scale. So we live here in the Coast Mountains. The Coast Mountains are unbelievably beautiful, and we're sort of nestled in this really awesome place to live. And I want to talk just first about the major mountain shaping forces. So there's sort of three of them. Compression-related uplift is pushing us up, creating mountains, building mountains, still active today. And that's happening at about 2 millimeters per year. So the mountains are moving up at about 2 millimeters per year, or 2 kilometers in the last 10 million years. They've uplifted. And then isostatic rebound by deglaciation. So as we'll see in a minute, we had really thick ice sheets on the landscape. And as those ice sheets melt and relieve the stress they put on the crust, that crust is elastic. So it's like a racquetball. You push on it and it stays there. And then as you slowly get rid of that ice, it slowly rebounds. And it's still rebounding from the last glaciation, which the ice melted back 10,000 years ago. I'll use this sort of a ballpark figure. And then glacial and fluvial erosion. Fluvial erosion are all these beautiful rivers we have ripping down the mountains here, are essentially what's trying to take the mountains away. So right now we're obviously winning the battle. We have these beautiful, huge mountains, and they're being eroded. So uplift is beating erosion in this area at this time. So these processes occur. You sort of go back to Geology 101. We've got the earth, we've got the solid core, we've got the liquid outer core, we've got the mantle, which is the solid material on which the crust floats. And so the crust can move around in these tectonic plates on the mantle. You're probably having flashbacks from some sort of earth science class you had in high school at this point. But these plates move around on the mantle, and they interact with each other. And so we're right here on this little mini Juan de Fuca plate interacting with the North America plate is what we're concerned with. And the mantle, even though it's a solid material, it's rock. It's not a liquid magma ocean. It's rock, but it's very slowly convecting. So it's slowly moving, hot material moving up, cooling off, and diving back down. And that's what's more or less the driving force for moving all of these plates around. And what we're concerned about is this Juan de Fuca plate interacting with the west coast of the North American plate. So here we have the Pacific plate moving west over to Japan, with Hawaii sitting in the middle. And we have this feature right here on the map, which is a spreading center. So the Pacific plate's going that way, magma's coming up, creating new ocean crust, and the Juan de Fuca plate is moving east-northeast towards us, the North American plate. Its relative motion is to the west. So this interaction is going to cause mountain ranges to be built. And we have a trench out here to the west. So we get mountain building as a result, we get volcanic eruptions, and we get earthquakes as a result of these processes. And this is a nice cross-section stolen from Clegg and Turner's book, and just to essentially show you this downgoing Pacific plate, or sorry, the Juan de Fuca plate going down underneath the North American plate is creating serious stress here at the boundary, and we'll talk about possible earthquakes from that. We have sort of the old basement rocks that are being pushed up as our mountains. And then we have volcanism that occurs as this material comes down. It dehydrates the ocean sediments that it brings with it, and that allows this solid mantle to melt. So it's sort of like throwing ice on... You'd probably throw salt on ice instead of ice on salt in the wintertime. Yeah. Salt on ice lowers, just like adding water, lowering the melting temperature of this material. And then those melts come to the surface in these beautiful manifestations, like Mount Garibaldi here in Squamish. So all those are contributing to this core of rock that's being pushed up, creating our mountains. So we're building these mountains, we're still continuing to build these mountains. The coast mountains are a very young mountain range. Some of the rocks in them are old, but the mountains themselves being lifted up were quite young. So a classic example, of course, of these rocks, the core of the coast mountains, is the Chief. Everybody, I would certainly hope, knows about the Chief. I just have to brag just for a second. This is the view from my office. I can see the magma chamber. My sole claim to that office is that the volcanologist has to be able to see the magma chamber. So, beautiful setting, of course, very large monolith of rock, one of the largest in the world, and it's a relatively sturdy rock. It's hard to erode granite. It's got a lot of quartz and feldspar, and then some micas and hornblends in there to make up its sort of coarse grain composition, and it sticks around. It's not easily eroded. And so it's about 100 million years old is the absolute age on the Chief. but it's only been in sort of in the coast mountains, exposed on the surface for much less time than that. It was crystallized, it was formed, somewhere between 15 and 30 kilometers below our feet. And then with these tectonic forces, it's been brought up and everything else has been eroded off the top of it. And now it's exposed for us to marvel at. And then it's intruded. You may have heard of the Black Dike going up the Chief to the top of the first peak. It's been intruded by Eocene dikes, and those are roughly 40 million years old. So we're still down on the tip of our fingers here in the geologic timescale. So here's just sort of a quick show of how we think the Chief formed, where you had magma coming up from below, from the subduction zone. Again, we're creating magma here. It's moving up into the continental crust, the North American crust, and it's ponding in the crust as a magma chamber, and then it'll erupt to create a volcano. Then we essentially, at 100 million years ago, that material crystallized, and then 40 million years later, 45 million years later, it was intruded by another magma to create things like the Black Dike. And then it was uplifted and everything stripped off the top, and we see it today as evidence for what happened, as our evidence for why we think these processes occurred to create the Chief. So that's just one example of sort of creating our mountain range. And then, of course, when you have a big mountain range, you're going to have weather systems interacting with it. So this sort of interesting interplay between tectonics creating mountains, and that will change dramatically climate. So you put big mountains in the way of these coastal storms, of course the precipitation is going to dump on them, and over time you'll create glaciers. And so ice is sort of the next phase, and roughly 2 million years ago, till about 10,000 years ago, we had intermittent episodes of lots of ice in these mountains. And so what evidence do we have for that? Because right now we can see ice on the Tantalus Range. We know there's glaciers at Blackholm. But what evidence do we have for the major ice sheets? Well, this is a bathymetric map taken from some of Pierre's work. And what it's showing is the depth of Howe Sound. And what you see, it's very shallow here at the entrance of the Squamish River, right up by Squamish. And then it really, really gets shallow right by Porto Cove. So the red colors are shallow water depths, the blues are deep water, and it really gets shallow here by Porto Cove. And so that's been interpreted as a moraine. So it's more or less a pile of rocks pushed by this glacier as it was advancing down the Howe Sound. And we call it the Howe Sound Fjord, which is a strange way to say it, because it is either a sound or a fjord, but that's okay. And so a fjord is more or less a glacially carved valley that's filled in with seawater. So that's some evidence for how we know that we have glaciers in the area. And then a little bit more tangible and locally, this is at the Malamute. So right across the highway from the Chief, there's that beautiful outcrop that they scraped off and put on display for the world for the Olympics. And so we have this beautiful glacially polished material with striations on it that signify essentially only a glacier could cause these striations. The rocks at the bottom of the glacier are under such weight, they're actually able to scratch parallel lines in the rock that when you're there, you can feel them, and they're moving, they're oriented north-south. So that's evidence for glaciation, clues in the rock record there, and then right at the same area we have glacial till. So this is all the material that the glacier chews up the existing rocks around it and deposits that material in these sort of gungy, clay-rich, very poorly sorted materials that you find around town when you're exploring trails and things like that. And then we also have sort of the bigger scale landscape features that show us that there was significant glaciation. So just walking around campus taking photos, you can see, it may not show up that well, but there's big hanging valleys up here, Lake Lovely Water and Echo Lake. They have these big hanging U-shaped valleys that these glaciers commonly create as the valley glacier is moving down to the south and the mountain glaciers are retreating back or moving down from the peaks. They meet each other, and that's why the valleys are hanging up there as all this melts away. You leave the valley hanging above the main valley floor. And then all these sort of pointy mountains, this is Mount Habrick, and then Alpha, are thought to have been above the ice. So that's why they're not all rounded off like the other things around. You can see most of these peaks in the foreground are rounded off by the glaciation. And so we have really spectacular evidence here in the Tantalus Range of an estimate of how thick that ice was. So if you throw a line on there, where everything below it is rounded off, and everything above is carved and carved into pointy peaks by these glaciers, you get an estimate of about 2 kilometers at one point of ice in our valley. So more or less 2 kilometers above us right now was ice. We would have been at the bottom of a 2 kilometer thick glacier. That's a significant amount of ice. That freaks me out a little bit more even than the big wave that's coming. So now we've built these mountains, we've filled them with ice, we have these wonderful glacial periods, and then we're also in the subduction zone, so volcanoes start erupting when we have all sorts of glaciers around. And that's when I really start to get excited looking at these deposits. Excuse me if I go too far. And that's been happening for about the last, what is it, a little less than 2 million years ago to about 8,000 years ago. We've been dealing with this fire and ice situation. So as you drive up to Whistler, you can commonly see on the sides of the highway these columns of rock. So these are at the BC Rail Quarry, just short of Brandywine Falls, and you see these columns of rock, and they're common in lava flows that cool slowly and are able to. It's called columnar jointing, and the joints are they go from the cooling surface. So usually the cooling surface, as you can see in the top photo, is the ground and the air. So it's cooling to the ground a little bit slower than the lava flow is cooling to the air. And so these cracks form, and they move from the top and bottom, and they commonly meet in a lava flow. So here you can see in the top photo from the Columbia River basalts in Oregon, those columns are nicely formed. They're perfectly more or less vertical because your cooling surface was at the top to the air and the bottom to the ground. Now you come to this insane place, and they're not vertical. They're going all over the place. They're curving. These are actually coming out of the wall this way. So what that tells us as a geologist, you say, well, my cooling surface had to be right here. Well, that doesn't make a lot of sense, right? Why would it cool and not flow into this valley? Lava flows, they flow downhill. Why doesn't it flow into that valley? Hypothesis is you had a glacier there. So the lava flow is actually butting up against a glacier. This particular outcrop, Bill Matthews thinks, was actually taking advantage of a pre-existing esker, sort of a river that forms in the bottom of a glacier as meltwater percolates down through and then flows. And the lava flow took advantage of that, and you sort of can map it out and start to see that you had this more or less subway through the ice already created by the esker, and the lava flow took advantage of it. So really neat stuff that gives us direct evidence that lava flows here were interacting with the ice. So normally a lava flow, as you can see here from Opal Cone. So Opal Cone, if you hike up to Elfin Lakes, it's just sort of on the right-hand side of Mount Garibaldi. It last erupted at about 9,500 years ago. At 1,700 meters of elevation is where the cone is, where the lava flow came out. And you can see right up here is the source of the lava flow, and it came down the valley, actually redirected Ring Creek. It's called the Ring Creek lava flow, and almost made it into town, almost made it to Valley Cliff. It's just sort of perched right up there, and actually really neat. That's where we get our the town gets its water. We have a great water supply for drinking water, and they've drilled wells right here at the bottom because all the water comes in. This lava flow is very porous, and so the water percolates down to the bottom of the lava flow, and then is capped and flows down the valley and stops here. And we drill and take advantage of this nice perched aquifer of really fresh water. But the point of this is that lava flows commonly come down the valley as far as they can, and they're gravitational. They'll just flow like water would down a valley. And so here we go from 1,700 meters elevation where it erupted. It made it all the way down to 250 meters elevation before it stopped. It's a spectacularly long lava flow for its type. And you can just see it here on Google Earth, starting up here, just sort of filling in that valley as it comes almost all the way down to town. So this is the lava flow. And you can sort of see some of the features. It has levees, just like a river would, and then compression causes these arcuate shapes on it. So you can trace it all the way back up to that opal cone. But we have other lava flows in the area. So this is Clinker Peak near Mount Price, and you can see that same lava flow looking thing, levees, compression ridges, very similar in geochemical composition to the Ring Creek lava flow. So there's no reason that this lava flow, which erupted at the same more or less elevation, 1600 meters elevation, there's no reason it shouldn't have flowed down into the Cheekye Valley. Below, this is Garibaldi Lake here, below this lake. But it stops right here, and it's also stopped in this very precipitous cliff that's been called the barrier. You can also see this lava flow comes down, and the levee broke at one point, and you can see this is a little lobe of lava flow that goes right now into the lake, and there's another lobe here, and then this is all the same composition lava as this. And so more or less Garibaldi Lake wouldn't have been there without a conspiracy of geologic events. So this should just be a mountain valley like we have hundreds of around here. Glaciers up here melting, water rushing down the valley, down the mountain valleys into the big valley and coming out, eventually out of the Squamish River into the Sound. But now we have this tremendous lake. We have 3 trillion beers up here that are trapped because this lava flow essentially dammed the valley, and those glaciers kept melting and the rainfall kept filling in the valley, and now we have Garibaldi Lake perched up there at 1,400 meters of elevation. So here's a few photos of the barrier from different angles. This is the barrier here taken from across Highway 99. This is Black Tusk up here. And you can see the barrier is this valley-filling lava flow right here. Now the Ring Creek lava flow, same composition, is about, 30, 40 meters thick. The barrier lava flow is 250 meters thick. And it started at 1,925 meters elevation and only made it down to 1,200 meters elevation because it hit the valley glacier. So there's a conspiracy of events. We have all this ice in the valley, and then we have mountain glaciers that are retreating. So when the glaciation came to an end, when the climate warmed up, the valley glaciers up in the mountains, the mountain valley glaciers, are thinner and more easily able to retreat because they don't have as much ice mass. Down here in the valley, this was still full of ice. So that lava flow erupted, the Clinker Peak erupted in this ice-free window at between 1,300 and 2,000 meters elevation, and it was able to flow along the surface until it came down and hit that valley-filling glacier. So this is from Matthews 1952, the paper he wrote on the barrier, sort of showing we have a valley glacier, big valley glacier, the 2 kilometers thick of ice, but we have this ice-free window where the lava flow is coming down the slope as it should, but it butts up against that glacier, and so you have all sorts of cool steam and little explosions going on. And then, of course, you over-thicken that lava flow, way thicker than it should be, because all the lava coming from behind it, instead of being able to flow down the valley, thickens it. And so it just keeps piling up and piling up and piling up until it stops and solidifies by cooling, and then that valley glacier eventually melts away with the warming climate, and we're left with this very unstable 250 meter tall cliff. If you've ever been up there and waited for more than a few minutes, you'll hear and see rockfall coming off of it. So volcanic materials are notoriously unstable on the Earth's surface. They don't last very long. And also, when you interact them with ice, they're even more unstable, because you're taking something that's 1,200 degrees, 1,000 degrees for these rocks Celsius, and cooling it very quickly against the ice. So a very unstable system. And because of this, it's dammed the valley, and Garibaldi Lake is formed. One of the coolest things about the barrier is that Rubble Creek, which goes down here into the Cheekye River, crosses Highway 99, is actually percolating out from below the barrier. So we think that it's Garibaldi Lake water that's finding its way down the old Paleo Valley surface, and you might think of it as undermining that dam. Yeah, awesome stuff. And I'll just go real quick. I have a photo of that so as you're walking up, if you can see, this is the barrier, this really thick lava flow. This is a big scree field coming off the barrier. And then right here are the springs of Rebel Creek. So Rebel Creek is just coming out from right underneath the dam. And it's coming out at about 3 cubic meters per second is the flow rate. So that if you've been to something like Ring Creek recently, that's kind of the amount of water that's continuously coming out of Garibaldi Lake beneath the barrier. And like I said, I have a new project to start mapping that area, and when my permit gets approved, we will be mapping the lake bottom with sonar to get a real sense for what that paleo valley looks like, and get a much better sense for what the whole dynamics of this system is. So that's not the only thing that the good fun stuff that happened with eruptions and ice. Let's look at here at a few Cascade volcanoes. So down in the US we have Mount Hood. You can see the little rectangle of skiing that they do right here in the snow in the summertime. This was a field trip in September. But we have this nice conical shape, classic Mount Fuji style Cascade, in this case Cascade volcano, but subduction style volcano. Then we have this weird funky looking Mount Garibaldi. And then we have the classic Mount St. Helens, which again looks different for a whole different reason. So this is sort of a classic subduction volcano that's built up over time of different layers, exact same mode of formation as Mount Garibaldi, and then Mount St. Helens just decided on May 18th, 1980 to get rid of the upper 200 or 2,000 meters or so of its peak, and we just had a chance as a class in September to hike up here, right to about here, and the only advancing glacier in the lower 48 of the US is in the crater of this still active volcano. Fascinating. The snow blows over the top, and at just the right aspect that it's actually accumulating, and that glacier is growing. I was there 2 years ago, and I was there this year, and it's significantly down valley. It's starting to come down these big erosional valleys. So a fantastic place. But the real point is, like, why does Mount Garibaldi look all weird and funky? There's not enough ice that's up there to have carved it like this, so there must have been some other reason. So you can sort of think of this as what it maybe should look like, and here's what it looked like. So why why does it look that way? We think it's something called a supraglacial volcano. Well, what the hell is that? Supraglacial. Okay. If you look here, another photo taken from Elfin Lakes. I was told that fixes it. There we go. Taken from Elfin Lakes, you can see the layers of rock in here, these nice colors, ochre and pinks and grays of the Peak of Garibaldi, and those are all the flows that created this edifice, this mountain. And so what they think is the edifice, or the mountain itself, was built mostly by pyroclastic flows, and we know that because of the layering. And some of those flows erupted onto a glacier. So there was a glacier somewhere up here, and those flows erupted onto the glacier. Well, of course, when that glacier melts because of the climate temperature increase, those lava flows aren't going to sort of jut out and defy gravity. They're going to collapse into the vacuum, because we have a very gravitationally unstable system. There's no slope, there's no toe slope support here. And so this quarter or so of the mountain is going to come right down the valley and end up, I don't know, 200 meters that way. The Cheekye Fan. And so we have significant local geography because of this fire and ice. Erupting volcanoes interacting with these ice. And they create these unstable features that geologically are all going to collapse. And we just sort of hope they don't all happen while we're living in this great place. Right? So if you sort of look around, we have this gravitationally unstable mountain up here, and we have really steep slopes, and parts of them are very unstable. This was a field trip where, hiking up the Chief, we encountered a huge boulder that had taken out part of the stairs there. And so not only just the volcanic slopes are unstable, but just gravity is working away, trying to break these mountains down. And so what's our evidence around here for collapses that have happened in the past? If I'm going to stand up here and start spouting off about bad things happening, we better have some evidence that it's happened before. And so we can look at a couple of particular places that they're peculiar. They're not the way they're supposed to be. So one of those is the Ring Creek gravel pit, right? This is the Quest soccer field right here. Just below this, if you go down the Mamcram, the dirt road, you cross by a gravel pit that's really neat. And then this is the Garibaldi Springs gravel pit, which is right here by the old Garibaldi Springs golf course, which is really not far at all from where we are right now, just probably over here. You can easily walk there. So we have something in you learn in Geology 101, the law of original horizontality. So when the Squamish River brings sediment down, it's going to lay it down flat. And that's the rule. That's the law. So sediments are always laid down flat, like this. But we see in this gravel pit, we have sediments that are certainly not laid down flat. They're laid down at a significant angle. And you can see the stratigraphy there at a significant angle, and then it goes flat. And so we try to figure out what the heck is going on there. As a geologist, you're acting as a detective, you're looking for clues, and this is sort of a clue that stands out at you because it's strange. It's not supposed to be this way. So the idea is, in the geologic record, we see things where the beds aren't flat, and it's thought to be as river water is entering a large sort of stagnant body of water, so like at a delta where faster moving water enters the ocean, there's a little area where the law is broken, and these sediments can deposit on a slope. And we call those foreset beds. And then these are bottom set beds that are flat, like they're supposed to be. Now, this is the model of an ocean. So this is what the Squamish River should be doing. But at the Ring Creek pit, we're up too high of an elevation. There's no evidence that the ocean sea level was that high. So we couldn't have been depositing these into the ocean. So we need another source of water, another mechanism to have water there. And so, really creative solution is that we must have still had this valley glacier. So this sort of Squamish Cheekye glacier was still in the valley melting away. And so we must have had that acting as a dam and creating a little lake right in the area of these gravel pits. Essentially, that's why the gravel pits are there, because that's where the gravel was deposited by the streams rushing off the melting glaciers up here and water depositing from glacial outflow into this big lake. So pretty neat, thinking about a lake perched up, at the elevation just below Quest at one time because it was dammed by this valley glacier. If you look in detail at those sediments, it's really neat because you can see a very sandy layer, really fine material, must have been very slow-moving water with a big boulder in it. And they think things like that, you must have had a boulder that was rafted on top of the lake because it was in ice, a little iceberg. And of course that iceberg melts and that boulder is going to go straight to the bottom and deposit in these very fine materials where it doesn't really belong. So just awesome place to live, awesome place to look at the rocks as you drive by them at 50 kilometers an hour and things like that. And so another evidence for collapse is the Cheekye Fan, which I talked a little bit about earlier. 1.6 cubic kilometers of material. So that's a lot of material. A 1 kilometer by 1 kilometer by 1 kilometer cube would be 1 cubic kilometer, of course. So bigger than that. Lots of material has come from the slopes, the toe slope of Mount Garibaldi when the ice melted, down here down the Cheekye drainage and created this big fan of material where the dump is and where the airport is and where pressure to develop. And so you can see here, this is an alluvial fan from Death Valley, and it happens when very fast-moving material comes out of a steep mountain valley river system and deposits on a relatively flat slope, and it fans out. So very similar in shape to what we see here, the Cheekye Fan. Sort of a modern analog to that fan is, if you remember, in August of 2010, the second largest landslide in BC history was up at Mount Meager, a Cascade volcano itself, right up back here. And you can see the big scar of this landslide coming down this valley. And it was a tremendous amount of material deposited in a matter of minutes. So these debris avalanches are incredibly fast and dangerous, and commonly sometimes a hot slurry of mud and big rocks and trees and water. This one happened because of the unstable slopes of this volcanic region have been stewing over the years. There's been some geothermal exploration up there to see if we can create power from the geothermal, but it's been weakening the rocks. And then there was a situation of a big storm, and too much water was held up by a snowpack up here, and the whole thing gravitationally gave way. And there was this tremendously large, it's very hard to show in a photo just how big this thing is. And so in mapping the local area, we can see sort of this evidence, mostly older than 6,000 years before present, but you can see this big fan of material. We know that it's from Mount Garibaldi because it has the same composition, the same geochemistry. They're volcanic rocks that came down from this area and just ripped through the Cheekye drainage down into the valley. Another smaller little part of the Cheekye Fan came down more or less down Jack's Trail, if everyone knows where Jack's Trail is, and then tried to make it into the valley there, just right across the pedestrian bridge, which I guess is right over there. But it got stopped by ice at the time. And you remember we talked about these jointing features, where it goes from the cooling surface in. So when you have a block of material, the cooling surface is all around the edges of that block. If you look at this particular block, you have these little joints all around the edge. Some places you can see them better than others. So that implies to us that the cooling surface must have been all the way around this block of material. And if you've ever picked up a jointed piece of material, it's very weak. If you dropped it from here, it would shatter on the ground. So there's no way that this came down the slope at 150 kilometers an hour and survived. So it must have cooled and jointed in place, in the deposit, all the way down here in the valley. So that's evidence for at least one or two of these big debris flows from Mount Garibaldi being hot, being from an eruption. And so we'd like to take a little closer look at this deposit to see just how extensive it is and how much of this material must have been sort of active volcanism on this ice while it was giving way. So pretty fascinating little things you can find when you dig a hole in the ground around here. Right, so let's go back to this 150 meter tall wall of water that's going to arrive right after I get back up to Quest this evening. So the sort of the fate of the barrier lake, which is right here, Garibaldi Lake, and if this sort of does collapse, or has a smaller landslides, you can dam the Cheekye River, and Daisy Lake Dam is right just north of where Rubble Creek crosses the highway. So significant potential issues in the area, and there was a town site, I think it was called Garibaldi, just across the highway that was more or less moved by the government. People had to move away. They moved north to the Black Tusk area. And so what you can see here is the mapped deposits of landslides from the barrier. So Garibaldi Lake is right up here. This is the edge of Garibaldi Lake. Here's the barrier, and rocks have fallen from the barrier down into the valley, and you can see how extensive they are. They actually go right up to the dam, which is right here at Daisy Lake. So if we had another significant landslide, you might start to worry about this river, the Cheekye, being dammed up, and of course overfilling Daisy Lake, and that overtopping the human-made dam, and all that material rushing down the Cheekye River, of course, into Squamish. Okay, so lots of potential for collapse. More ways than one. So what's going to happen in the future? Is this going to happen? Should we worry about it? Should we just cash in, what do we call them, RRSPs here? Just cash those babies in and buy a new mountain bike, enjoy it? Or should we go to work tomorrow? No, you can't use me as an excuse, especially for class. And so just sort of looking here from the top of the chief, next time I suppose I should have one from the top of the gondola, if they give me a free pass or something. And we have, again, all these natural, unstable features that really shouldn't be there, sort of conspiracy of geologic events that we're able to see a snapshot of during our lifetimes. And it's really awesome to see all of this stuff is going to get destroyed and fall down into the valley on the geologic timescale. But in our lives, we get to enjoy its beauty. And of course, I haven't even touched on all these awesome rivers that come and flood the town from time to time. And so, are these things going to happen again? So let's look at some of the hazards that we're dealing with. We'll just look at some numbers. I didn't do any real statistical analysis or anything like that. That's someone's job who knows how to do those sorts of things. But Opal Cone last erupted, between 10,700 and 9,300 years ago. So that was one of the last major eruptions in the Garibaldi volcanic complex. So you can sort of think about that as, does that mean it's going to erupt again? Well, potentially. The subduction zone system is still happening. We're still creating melts below the surface. Just south of us, Mount St. Helens had erupted recently. And so this is sort of the American Cascade volcanoes from the USGS. And of course, we're just right up here at Garibaldi. But you can see over the last 4,000 years, sort of the frequency of eruptions in the Cascade range. Some certainly more active than others, but there seems to be some, random eruptions happen from time to time. So I wouldn't say that Mount Garibaldi is shut down. It just is not in one of these, is not one of the more active volcanoes. It would be sort of not having erupted from something way over here. But that certainly doesn't mean it can't reinvigorate. And there was a recent eruption in Japan. Unfortunately, a bunch of people were killed, but that was a volcano that they weren't concerned about erupting, and lo and behold, it did. And so, what about Garibaldi collapsing and sort of feeding this Cheekye Fan and creating that hazard? How often does that happen? Do we need to worry about that? Do we need to plan for that? And so a lot of work has been done by Pierre to look at these events. One of the coolest things I think he did was he took he saw a damaged tree that was still alive. Right, if you go from Fergie's just up the Cheekye, there's areas where you can see damage from these big landslide events. So what is it coming down here? Here's Highway 99. So material coming down the Cheekye here, and these are his sample sites. And one of the coolest things he did is he took a chainsaw wedge out of that tree. And how do you date these sites? Well, he was able to count tree rings, and these are scars from big boulders hitting that tree. And then, of course, the tree is able to heal itself and grow around that scar. And so he was able to get dates on 1945, 1958, 1991 of big, significant events coming off Garibaldi into the Cheekye Fan. And of course, we worry about it damming these rivers and creating subsequent floods. So what he found is that 9 events in the last 200 years have happened, and 7 of those have come all the way down and crossed the Cheakamus River, where the Cheekye and the Cheakamus meet right here at the bridge. 7 of those have crossed that river, so made it down to town. So you have sort of a 22-year interval, and just 1991 was how long ago? 23 years ago? Oh, the big one. Is the barrier going to collapse because of the next big earthquake? Well, maybe, but we'll have all sorts of other problems as well. So is this Megathrust type earthquake going to happen? So as this oceanic plate, if you remember, comes down, there's certainly friction between the overriding North American plate and that downgoing subducting slab. There's some really neat research being done by the Geological Survey of Canada over in Victoria. And more or less what they're seeing is they're seeing Vancouver Island, the North American plate, it's on the North American plate. It's supposed to be moving west. It's actually moving back to the east. So it's being coupled to the downgoing slab and moving with that slab. And what they're worried about is it rupturing. And so Vancouver Island is going to say, I'm going to go back to where I'm supposed to be. So you have a huge amount of uplift, and you have a tremendous amount of energy released as Vancouver Island decides to go up by 3 meters in a quarter of a second. And of course you're going to have probably local tsunamis and that sort of thing. And then on the east of Vancouver Island, the land is going to subside, and it's going to be bad. So how often do these things happen? Well, this is a figure from Clegg and Turner's book, and they sort of see them happening in kind of clusters of 3. So we had one here, 1000 BC, and then another cluster here just before 1000 AD, and then January in 1700 was the last big one around here, seen through tsunami deposits on Vancouver Island and also in Japan, correlating to get a pretty good age bracket for that. And so are we in the next sort of in one of these clusters of 3? So was the 1700 quake the start of a cluster? If so, we have probability-wise here,
where we have time on this axis from 1700 to today. We can see that the probability of a big one happening would be about a 30% chance in the next 50 years. So that puts at least a number on something to give you an idea when the big one's going to happen. But if you think about it, the barrier was certainly there during all of these earthquakes, all of these big subduction-related earthquakes, and it hasn't gone yet. You might argue that it weakened it, but okay, so that's sort of the local geological story. Of course, there's lots more theory and other really cool places to go and see, but I just sort of wanted to recap that as mountain, sort of the mountain building events, creating that ice, the awesome volcanic eruptions, interplay with that ice, creating these very unstable, steep slopes that gravitationally want to come down in the valley. So, are all of these bad things going to happen? Absolutely. In geologic time, if I can make her come back up here and hold her arms, that'd be funny, but I won't do it. They are going to happen. Do we need to worry about them? Yes, we do. Should we worry about them? Probably not. I think the bar is still open. So, in the meantime, I think we should just enjoy our local environment, and thank you very much. I appreciate your attention. If there are any questions, I'd be happy to deflect them.
You keep asking and don't get the answer. Does anyone know when the witch on the chief occurred?
Sorry, when the what on the chief?
The witch, you know that
The badge. The badge, the chief.
Badge, I see it as a witch.
The back? Sorry, the back?
There's a witch or a badge on the chief, and he's like to know when did it happen.
Is it white?
Yeah.
Ah, so that must have been a boulder, a huge boulder that now people climb on at the bottom?
Earthquake in 47.
That fell off? Earthquake in 47? So that's when they think that boulder came off the chief? And that, the slab, gotcha. 1947? Yeah, and so and then geologically, you tried to look into it. It's a different color because it hasn't yet been stained by the sort of surface deposits, and so that the locals say 1947. Well, I'm not a local yet, but I want to be. So 1947. Anything else? Any other questions?
What causes ice ages? Huge temperature changes.
Yeah, so the question is, what causes ice ages? What causes these huge temperature changes? And you can sort of think of on long-term scales of three main things. Let me see if I can remember this. So if you have the orbit of the Earth around the Sun is an ellipse, and sometimes that ellipse, think of it as squashing, and so at times our rotation around the Sun is marginally farther because that ellipse squashes, and if it's more of a circle, it'll be warmer. And if it gets if it's like more of a squashed ellipse, we get farther away, so the temperature is cooler. And then the rotation of the planet, sometimes it, if you think of it like a top, it doesn't rotate perfectly, and sometimes it wobbles more than others. And so your angle, so sometimes that wobble causes the deflection of the sun's rays to be not as direct on the Earth. And then the tilt of the Earth changes a little bit over geologic time, between 21 and 24 degrees or something like that. So you imagine when it's more upright at 21, the rays from the sun are more direct, and then when it kicks back to 24, you have a less direct sunlight, and so you have cooler temperatures on a grand scale. And then other smaller glaciation events must have been caused by large volcanic eruptions in the geologic record, where you sort of fill the atmosphere globally with ash, and more or less sunlight gets to the Earth because those ash create aerosols, and they're called sulfate aerosols, and they have more or less the same wavelength as the incoming solar radiation. So they're very efficient at bouncing that radiation back to space, so we get less solar radiation down here. So those are ways in which we get this cyclical pattern of warm, cold, warm, cold. And then there's lots of research and ideas about since 8 or 10,000 years ago, have we, by deforestation and agriculture, been moderating that or not?
Thank you.
Yeah, sure. Yeah.
How recent are the castles on the other side of the Squamish River?
Oh, the castle lava flows on the other side of the Squamish?
Yeah, and in front of the peaks.
Yeah, so and they have beautiful columnar joints in them, and they have those jagged peaks up high.
Yeah.
I don't think we have an age on those. I was just having a meeting with my former supervisor at UBC, and that's one of his project ideas for a student coming in. I would, if I had to ballpark it, I'd say 30, 40,000 years ago would be a number I would make up to answer that question. Sorry?
Garibaldi's 10,000, and so they're...
Yeah, the most recent eruption in Garibaldi was 10,000. So at the same time as some of Garibaldi was building up, that I think those eruptions occurred, and then whether or not it's related to Watts Point, which is also volcanic across the sound, is yet to be known. Lots of great work to be done around here.
You didn't comment to any degree on the Black Tusk and the crater beside it, nor Table Mountain. And I wondered, was there any particular reason why you left them out?
Because it's my plan to go up there and map them again. So I have to leave something for the next talk. But the Black Tusk is more or less the core of an old volcano that's been eroded away. Sort of think of it as the neck, the conduit of the magma or the lava coming up. It doesn't always all make it to the surface, so it's harder to erode that material, and so it's more or less left over there with all the fine-grained particulate material washed away. The table is absolutely fascinating because it's thought to be mostly erupted underneath the glacier, and then when it comes up, it's flat on the top because it's thought to have broken through the glacier, and then the lava flows are flat. And then Cinder Cone, I think, is the one next to Black Tusk. There's a little eruptive center there, and so those are two of those three areas. The Cinder Cone and the table are on my list for the next 5 years of mapping Garibaldi volcanic complex. So, yeah. I mostly didn't talk about them today because they're not. If they did collapse, they wouldn't make it into the valley. So we're not too much in danger from that.
And Mount Cayley and Fee, there's some structures in there. What is their relationship in age and timeline to...
Yeah, so the question is Mount Cayley and Mount Fee they're erupted underneath the ice, so we know that there's substantial ice in the area, so we know they're older than 10,000. And I had a colleague who did her PhD on that, and I've forgotten her results. But I would say in the last, 50 to 100,000 years was when those volcanoes were active.
With that many volcanoes, do they all come from one fault or one pool, or are they separate streams?
Yeah, there's been some, so the question is, are they all related? And in one sense, yes, they're all related from the same subduction-related activity, magma generation, but they don't share small magma chambers. So the little magma chambers that come up in the crust, they have their own pockets of magma to feed their eruptions. But at depth, they're certainly related. And there's been some real recent studies done on the geochemistry to try to fingerprint exactly the processes that are going on there. And so I think some of them are certainly related from the same magma source, and I believe some of them aren't. And they're still unraveling that story using geochemistry and isotopes and in the lab at UBC. Yeah?
How many eruptions have there been in Mount Garibaldi in the past, and is there a change in composition through time?
Yeah, so the question is how many eruptions have there been at Mount Garibaldi in the past, and has the composition changed through time? Classically at these subduction zone related volcanoes, the composition varies quite a bit, all the way from basalt and all the way up to rhyolite. I don't know if you know about these compositions. And so we more or less find almost all of those in the whole volcanic system, but what we sort of see exposed now is mostly all rhyolite pyroclastic flows, explosive eruptions, and the composition, I would have to say, hasn't changed. Or if it has changed, just been very minor changes in the composition. There's been no significant changes that you could tie a specific geologic event to or change in the system. Just minor heterogeneities in the source of the magma would be all that has changed about its composition. It's not evolving towards something different or anything like that.
Over what period of time?
I think that, and again, I'm ballparking here because there haven't been too many dates on some of the more, the deeper rocks, but I would say over the last 100,000 years.
So you touched upon this a little bit, and I'm wondering, as a non-geologist, lay person that looks at the Cascade Range, it's my perception that Rainier, Hood, and Mount St. Helens are much more active than what's north, and I'm wondering if that's just, if there's any hypotheses as to why that is, or if it's just that the north is less studied.
Well, I think that certainly those volcanoes are more active than ours here in Canada. So the question is, are the US Cascades, they've been erupting more recently than the ones in Canada. And if you'll notice, if you look at a map of the Cascades, they turn at the border. Right? So it's sort of this nice straight line, easy to explain, straight line. We got the subduction zone coming from the west, line of volcanoes, Washington, Oregon, California. There it hits the San Andreas Fault, no more volcanoes because it's a fault. And the plates are sliding past one another. But right at the border, more or less, probably an influence of Vancouver Island being there, that range turns. And so there's ideas in the subduction of the plate. That turn is actually causing the plate to split apart in the subsurface. And that split is not allowing for the same the sort of cascade-style eruptions to occur. But north and a little bit east, there's been the crust has been extending, and magma has made it up in the last couple hundred years. We have very young volcanic deposits in British Columbia that are different than the cascade style, but they're still related to that system. So I think there's probably something going on with the reason for that turn that's causing the plate to get all jumbled up down there, and different volcanism is occurring. So there's still been activity, just not at these volcanic centers.
Where are those recent British Columbian?
Yeah, have you ever heard of Nazca Cone? That was a few, less than 1,000 years ago. And then sort of this vague area of northern BC, sorry for less detail. Mount Ziza, thank you very much. Very young volcanics at Mount Ziza in the region around there. And where is there a geographic landmark around there that? There's not much up there. It's beautiful. Yeah. North of Prince George, yeah. Right. Yeah. So still a rich, active volcanic history in British Columbia, but most of it's been in very rural areas and not in these sort of classic cascade eruptive centers.
And Sky Pilot and Haybrook are of the same nature as Atwell and Atlas?
So Atwell is part of Mount Garibaldi, so it's volcanic. Sky Pilot and Tantalus and those mountains are the core, they're either granites like the Chief, or they're older material that's been pasted onto the continent through a process called accretion. So they're actually just bedrock that's been eroding away with these glaciers. They happen to look similar in shape, but their origins, their genesis is different. Yeah, last question.
Yes.
Sorry?
All these volcanoes that stretch from Shasta up to, Quane and Garibaldi, they're stratospheric. Are they all common in the qualities, or do they have a uniqueness? It's like a line, and as you say, it comes off the same plate.
Yeah, so the question is, are all these cascade volcanoes common in their characteristics? I think the answer to that is sort of generically, absolutely. They're very similar. If you compare them to Hawaii, or something like that, a totally different type of volcanic system, they're very similar. But each one has its own sort of unique characteristics as well, and mostly in landforms, how it interacted with the landscape around it. But I would say that in general, the cascade-style volcanic systems, you could go to them and you would find very similar things, in a different order, in a different shape, but very similar geochemistry and the nature of the deposits. All right. One more?
You know what, actually, I've decided, you know what, I'm so glad you've enjoyed Dr. Steve Quane this evening, but if you would like to ask him another question, because we actually have a meeting after this, please buy him a beer. He would love to talk to you if you bought him a beer. So give everyone a